Hi everyone, welcome to this supplementary video. So this supplementary video is about example 8.14 in the book. And we had briefly discussed this problem in the last lecture when I had mentioned about how I was not able to generalize the solution and make it something which is more general. And so that is what I want to discuss. We also didn't discuss the full solution in the class. So the hope is that this video will help you do that. So some small differences from the example given in the book is that I will assume here that laminar flow is valid, and I will tell you why I did that a bit later. This is just to make the calculations a bit easier and to get actually something tractable. And the second thing that I will do, which is different, is I'll assume different lengths, diameter, L1, LD1, L2, D2, and so on. So the book actually uses same diameters, but I don't want to use that assumption right now. And I want to generalize, but I do want to assume a different laminar, a different kind of flow, a laminar. The book uses a turbulent flow. All right. So what's the problem? Just in case you forgot, this problem is about the 3-tank problem, in which essentially one tank is at the top, the A tank here, and it goes and tries to have there is a pipe connection. There are 3 pipes, L1, L2, and L3, with diameters D1, D2, D3. And what's really going on is that the flow is happening from A to B or A to C. But what is not clear really is whether the flow is going into B or coming out of B. So there are two scenarios. So the two scenarios are that flow is happening from, so flow is like this in terms of flow rates. So scenario number 1, where this A is diverting water into B and C. A here, B and C here. Or I have a different, the second scenario is where A and B are bringing in the water and then it's going to C collectively. Okay. So A, B, and C. Okay. So that's essentially the sort of the idea here, is that there are two scenarios and we don't know which scenario we are in. So what I really want to do in this particular video is to show you how can we eventually decide that which scenario we will be in. Okay. So this is a slightly more complex problem. I should note that, but hopefully if you understand this, you will really understand. Another thing that we'll assume, which we have done before, is we will assume that tank areas are large. Okay. And you will understand this very soon why tank areas are large. And that height is roughly constant in these tanks. Okay. And water level remains unchanged, remains approximately constant. And you might say, well, how can that be possible? That is obviously an assumption. If the water keeps on flowing, then the top tank might start to drain and so on. But so that's a different scenario. We're not discussing that. We'll assume that at a moment, we'll assume that the tank is really large. So just even small little change needs a lot of volume. And that we are not essentially considering the scenario where things are changing with time. Okay, so that's a separate problem. We are not discussing that. You can add those complexities. Those are not that difficult to add, but that is currently beyond the scope of this course. Just wanted to mention that. Okay, so what do we want to do? So in scenario 1, essentially we will be doing scenario 1. We'll be doing Bernoulli's modified Bernoulli's equation 2 times. And yes, there are no minor losses. This is the same assumption and as in the book as well. No minor losses. Basically, there is no bend and all loss. We can ignore. The basic loss is just the major loss through the pipes. Okay. So with that, scenario 1 will focus on that first. And so here we have inlet as A and outlet as B, that is A to B. Then we have A to C, inlet A and outlet C. Okay. So now this is very important. I'm not writing, be very careful here. I'm writing PA. I'm not writing P. I'm writing the balance here. A B, the inlet and outlet, and A and C, inlet and outlet. I'm not writing the balance in the pipes. Pipes are just where the losses happen. The balance is between A and B, and this is done purposefully so that we can simplify and do the calculation very fast. So you'll see what I mean by that. So we have PA by gamma, right? Then we have UA square by 2G plus H of A is equal to PB by gamma plus UB square by 2G plus H of B. And then the water, so this is between A and B. So the water flows from pipe 1 and pipe 2. So I have to sum the two losses, and these are the major losses only. So I'll say U1 square by 2G into FL by D. So that is F1 L1 by D1 plus U2 square by 2G is F2 L2 by D2. Okay, so that's the point. So the velocity is actually at the top of the tank, and because the cross-section area is very high, we can essentially just say these velocities are approximated to be zero. The pressures are atmospheric pressures, or we can say in gauge units, they're exactly zero. So you can ignore them, or we can equate them or ignore them, either or. You can say PAT, and then the two sides will cancel. So essentially what we get is HA minus HB. So this is A to B. A to B, HA minus HB is equal to U1 square by 2G times F1 L1 by D1. This U2 square by 2G F2 L2 by D2. Okay. So all it is saying is that there is a potential difference between A and B. So there is a potential difference between A and B. By the way, we'll assume C to be zero, again, which is a reference potential at C is equal to zero. You can also have a finite value, but doesn't matter. It's just a reference value because it's always taken from a reference value. So we'll assume C to be the reference. So HA minus HB. And then we say, oh, well, that has to, there's a potential loss in kind of potential energy. So where's that energy going? It's going in the viscous losses. And the viscous losses are the two pipes that are connecting the A and B. Now with that, before I go further, note that these are all laminar pipes. So I can say F1 is 64 by RE1. And this is equal to 64 by rho U1 D1 by mu1. So mu1 goes on top. Okay. And so this implies that U1 square by 2G into F1, which is 64 mu1 by rho U1 D1 L1 by D1 becomes, so I've just substituted the value of 64 by R in a laminar pipe. It doesn't matter if the pipe is rough or smooth. That's the friction factor. And so one of the U1 gets cancelled. So now this is why I actually used laminar flow, because there one of the velocity square actually reduces to linear equation, and linear equations are easier to solve. So that was the precise reason why I was using laminar flow. You can do it with more generally with turbulent flow, but it's a mass and much more difficult to calculate. So that's why I've purposefully chosen laminar flow. And you can still do it for a more general scenario, but that's something that I'm not doing right now. And then there is a 32 here. So there is a 32, which basically 2 gets becomes 32. So you get 32 mu, not mu1, just mu. I just remove mu1 and by mistake wrote mu. It's the same viscosity everywhere. There is no difference in viscosity in the pipes. It's the same fluid. Okay. This becomes 32 mu U1 L1 by D1 rho D1 square G. Okay. And finally, purposefully, I will also write this as 32 mu into Q by pi Q1 by pi D1 square by 4. So I'm writing in terms of flow rate, and it will also become clear why in a bit. So I'll just multiply and divide by pi D1 square by 4. Sorry, not really. Yeah, I can just say Q into U1 by pi D1 square by 4. So this is U1 into L1 by rho G D1 square. And finally, all of this will give you, and you just take a second if you do it yourself, it's not that bad. what you'll get is 128 mu1 L1. Again, there is no mu1, just mu. If I write somewhere mu1, just ignore it. Mu L1 by pi rho D1 D1 4 times G times Q1. Okay, so this factor is what I will call as alpha 1. Okay, so this is just a resistance kind of factor because I'm trying to convert something from flow rate to height. It has some units, but we are not interested in the details of this. But as you can imagine, I will, if I do the laminar flow, I'll just replace L1 by L2, D1 by D2, and so on. So I'm just writing this as alpha 1. And this will essentially, I'm writing this as alpha 1 Q1 plus alpha 2 Q2. So this is the main factor here, where alpha 2, just so that everybody is clear, you can find it by using that alpha 2 will come out to be 128 mu L2 by pi D2 to the power of 4 G. Okay, so just the same, but for pipe 2. So essentially, what I reduce this to, was that I can write it as a linear sum of Q1 and Q2, but with the factors of alpha 1 and alpha 2, where alpha 1 and alpha 2 represent some of quantifies the losses in that particular pipe. In a way, it is like resistance, but slightly different units because we have, there is a row as well, before I forget, row here as well in alpha 2. And this is so that we can kind of compare left hand side to the right hand side. The units are slightly different, but hopefully this makes sense. Basically, every pipe is causing some loss, right? And so the flow rate it is carrying is multiplied with some coefficient, which is kind of converting it into head loss. And that coefficient depends on the viscosity, the length, the diameter to the fourth, and so on. And so that's why we get this fact. Now this is basically, now you can very quickly start to see what will go on. Now I can do A to C because the second inlet and outlet is in scenario 1 is A to C. So just to remind you, the scenario 1 is flow going from A to B and flow going from A to C. Okay. And so from here, basically we'll say PA by gamma plus UA square by 2G plus HA is equal to PB by gamma UB square by 2G. PC by gamma, apologies, PC by gamma plus UC square by 2G plus HC. And now the losses will be in the first pipe and the third pipe, F1 L1 by D1 into U3 square by 2G into F2 F3. Let me just write it again, U3 square by 2G into F3 L3 by D3. Okay, so this is essentially my system. Now PA and PC are same or both 0, you go get rid of them. Tanks are large, so we get rid of them. HC is equal to 0, that's the reference. So I simply get HA is equal to, and this we know we can represent in terms of alpha 3, alpha 1 Q1 plus alpha 3 Q3. All right, so all of this hard work essentially reduces for us in the simple form of HA minus HB. HA minus HB is equal to alpha 1 Q1 plus alpha 2 Q2, and HA is equal to alpha 1 Q1 plus alpha 3 Q3. Okay, so this is simply saying the potential difference is equal to the viscous losses. So we don't have to do the calculations again. Also physically, we can quickly see this makes a lot of sense because the kinetic energies and the pressure energies remain the same. This is the only difference that comes out. And we also know from the continuity equation that Q1 is equal to Q2 plus Q3 in this case. So Q1 is equal to Q2 plus Q3. Okay, so these are the three sets of equation and the three variables Q1, Q2, Q3. And so we can essentially basically, solve this problem. But now the main thing we should note is that we essentially want to be able to eliminate, everything and just write the answer for Q2, because Q2 is what we want to be positive. For scenario 1 to be valid, to be valid, Q2 should be positive, right? Okay, if Q2 becomes negative, then means the water is flowing in the actually the opposite direction. And so we have some issues in that case. So to do that, we can essentially try to start to eliminate the variables. So the first thing I can see is that Q3, I can write it in terms of Q1 and Q2. So it's HA minus HB is equal to alpha 1 Q1 plus alpha 2 Q2. And then I have HA is equal to alpha 1 Q1 plus alpha 3 Q1 minus Q2. And this is done so that we can then eliminate Q1 from the top equation as well. And so this becomes, and this implies HA minus HB is equal to alpha 1 Q1 plus alpha 2 Q2. And HA is equal to alpha 1 plus alpha 3 into Q1 minus alpha 3 Q2. Okay. So this is what you get. And now to eliminate, as you can imagine, to eliminate, essentially, should be multiplying this by alpha 1 plus alpha 3. And then I should be multiplying this by alpha 1. And I should be then subtracting so that I can cancel out Q1 and I can only get, I can then simply get the Q2. Okay. So let's do that. So I get HA minus HB into alpha 1 plus alpha 3 on the left hand side. And you can do this yourself a little slowly if you're not as comfortable with quickly doing this. It's not too bad. I'm just linearly solving the equation. And then here I get alpha 1 alpha 2 plus alpha 2 alpha 3 plus alpha 1 alpha 3 Q2. And finally, let's try to simplify this a little bit. So we have 3 terms remaining. So I only have alpha 3 HA minus alpha 1 plus alpha 3 into HB. And this essentially what I get is alpha 1 alpha 2 plus alpha 2 alpha 3 alpha 2 alpha 3 plus alpha 3 alpha 1. Okay. And please feel free to do this yourself. I have just maybe rushed a little bit, but this is really not bad. You're just solving for Q2. And this is what my value is. So the condition for Q2 is that this number should be positive in the numerator. The denominator is always positive because that's just alphas are always positive in the way we have redefined the term alpha 1, alpha 2, alpha 3. And so in this case, what we really need is alpha 3 HA should be greater than alpha 1 by alpha 3 by alpha 3 times HB. So this is the condition when scenario 1 will be valid. But if it is not the scenario, then we will not be able to get this to be valid. And that is something we should remember. Okay. So that's clearly like this is a condition. So this is not always true. There is a requirement of resistances. So when will be the case that we will see this not being true, because HB is obviously smaller. So what I really want is the numerator, the alpha 1 plus alpha 3. I want the numerator to be very high. So if the resistance in the first pipe is very large, right? Alpha 1 is really, really large. And that can happen if the pipe is really small, because alpha goes 1 to the D1 to the 4th. So if the first pipe is really thin, alpha 1 will be really large, and then it may not be able to compensate for the lower height of HB. Or when H1 and HA and HB are quite close to each other, in which case also the loss between the potential energy will not be that much. So this scenario can definitely fail. Okay, so now I know this video has been long, but I want to also discuss the second scenario. So let's also do scenario 2, and I'll not take that much time because now we can quickly do this. So I'm going from now A to C first, because remember from here, I will go A to C and B to C. Okay, so what you will get in A to C is simply HA, because HC is 0, so I'll not get that. HA is equal to alpha 1 Q1 plus alpha 3 Q3. And from B to C, what you will get is again HB is equal to alpha 2q2 plus alpha 3q3. Okay. And now I will not have q1 is equal to q2 plus q3 because I am having actually q1 plus q2 is equal to q3. I want the two flow rates coming from A and B to merge with 3. So I will have q1 plus q2 is equal to q3. Okay. So now let's do this analysis quickly. So I can write, because I want to eliminate again 1 and 3. So I will write this as q3 minus q2. Okay, so I get HA is equal to alpha 1 plus alpha 3 q3 minus alpha 1 q2, and HB is equal to alpha 3 q3. I've just reversed it so that you can see this alpha 2 q2. Okay, so I've just reversed them just to show you that we are doing the same process. And what we get is, now I will multiply this by alpha 3, and I'll multiply this by alpha 1 plus alpha 3. Again, then I'll add them. I'll do the same process like I was doing before. And so what I will get, subtract them. And so what I will get is HB into alpha 1 plus alpha 3 minus alpha 3 HA is equal to alpha 1 alpha 2 plus alpha 2 alpha 3. And you can try this on your own. I really encourage you to do this. Is what is Q2. And amazingly, as you might notice, that this is positive. And when this is positive, that means that HA should be less than alpha 1 by alpha 1 plus alpha 3 by alpha 3 HB. So if this is the case, then I will have this to be positive. And this is actually exactly the same condition, just the sign is flipped. In the top one, the sign is greater than, and the bottom one, the sign is less than, which makes sense. They're mutually exclusive. So it means that in one case, you may actually, once you flip the sign, you will get that. And also note that the flow rate can be exactly 0 in the second pipe. If you set the resistance such that, then the flow will actually just not happen. You'll just go from A to C, and you may not get any flow rate. When the exact balance comes, which is the equality sign, in which case neither scenario applies, and in that case the flow rate will be exactly 0 in Q2. Okay, so this analysis I wanted to show you, cover this analysis in detail, and hopefully you can appreciate some of the more advanced topics here and how different resistance is balanced and how water is always trying to find the path of least resistance. And so hope this video was helpful, and I look forward to seeing you in the next video.